the ones here in person and the Zoom room, to our seminar today. It's my pleasure to introduce my colleague Sonia Martinez from the University of California, San Diego, from the Department of Mechanical and Aerospace Engineering, where she's been for a number of years. And she's going to be talking about some of her recent work, which we're very excited, talking about performance metrics and defense strategies. But Professor Martinez received her PhD from Spain, from the Universidad Carlos III in Madrid in 2002. And then from there, she had a number of positions. She was a Fulbright scholar and a postdoc at UIUC in particular, and also at the CPSRC in Santa Barbara, where we met. I was a student at that time at that university. And since then, she's been at the University of California, San Diego, from assistant to associate to full professor right now. And she's also IEEE fellow. She received the Best Paper Award. And she's currently also, in addition to being associate senior editor for Automatica, she's also an editor-in-chief for a new journal that maybe you want to tell us a little bit about. So welcome.
Yeah, okay. Thank you, Ricardo, very much. And thank you, everyone, for joining this virtual seminar. It's a great pleasure to be here today. And so for today's talk, I'm gonna describe recent work on algorithms to compute performance metrics and defense strategies to measure and enhance network resilience. And so this is joint work with my former postdoc, Senju Liu, and also Professor Jorge Cortés at UC San Diego. Okay, and so for those of you who don't know me that much, so this is kind of a vignettes doing an overview of my work. I've mostly worked on the analysis and design of distributed algorithms for multi-agent systems that you can deploy to manage infrastructure networks or as multiple vehicle systems performing cooperative and estimation tasks. My technical approach to these problems are from nonlinear hybrid systems theory, as well as convex optimization and game theory. Initially, I also have this picture here. I also have some work on motion planning for underactuated robots and manipulators. Anyway, so if any of you are interested on any of these topics, feel free to visit my website and I'll be happy to talk about any of these with you later, if we meet, or otherwise, some other time. So, but today let's talk about cyber physical networks. And as you know, this type of networks, very large, are becoming increasingly pervasive. We are becoming more and more dependent on these networks for the management. Our society, relies on them significantly. And so we better make sure that they are protected and they are secure. Main challenges to make sure of this are basically that they are very large size, and so they are highly uncertain. It is not possible to know at all times, all of the state describing the whole network. They are geographically dispersed systems, and both of these conditions make of them, very vulnerable, right? They offer, let's say, a large attack surface, right, for adversaries to tamper with. And so what, what can we do about this? Well, for sure, something we can do is try to understand how they can be made more robust by computing or finding new metrics and algorithms that can help us measure and enhance their resilience. And so, this is an area that, as you know, is receiving lots of attention, and there are a few people at UCSC who are working on this topic. So this is our most, it's a set of contributions, more recent contributions to this topic. So let me start by discussing about network resilience metrics and how to compute them. And to fix ideas, consider a simple situation. You have a continuous time system described by some linear time invariant equation like this. Okay, so the matrix A is describing the system evolution and has a certain structure that is compatible with a certain graph. For example, you can think of a power grid and this graph being the edges of this grid, right? Now, this network may be subject to some attacks, and this very easily can translate into trying to break down, tamper with some of the links of the network. So this translates mathematically into a disturbance of the system matrix given in this way, where this disturbance, say, has a certain limits, right, given in terms of saturation bounds, but definitely, constrained to be on the topology of this network. And so what can we ask about? I mean, how can we try to analyze this? Well, first question is, well, will the disturbance be very bad, right? Will induce destabilization? Is it possible? Second question is, well, how much can the system really withstand before becoming unstable? Last question would be, well, can we design a defense strategy, maybe also in the form of fixing the topology? So it's a sort of topological defense strategy. So I'm gonna leave this last question for the end, and let's talk about these first two questions. And we are talking about stability, right? And given a disturbance, we have a matrix, and the way of quantifying this is basically looking at the spectral abscissa, right? This is the rightmost eigenvalue of the disturbed matrix, right? This is for a given disturbance, but if we are considering a possible collection of disturbances, right, then what we have to look at is this epsilon pseudospectral abscissa, which is the maximum value of these rightmost eigenvalues for a given energy budget, if you like, right, which is quantified by a Frobenius norm being less than an epsilon. And so, okay, that sounds good. Now, in order to say, okay, how much the system can withstand, what we want to be able to measure is this stability radius type of thing, right? So we want to find what is the minimum energy, minimum epsilon for which this abscissa, epsilon pseudospectral abscissa is going to become 0 or positive, right? That's it. Now, these are notions you may be familiar with. When you, in addition, impose additional constraints on the structure, right, of the disturbance, right, according to this graph that I mentioned, you also have similar notions. They have this additional structure in front of their name, but similarly quantifying what is the maximum value of the rightmost eigenvalue over here, and then this is the structure stability radius, which is the minimum epsilon for which this new type of abscissa becomes positive or 0. And so this is what we would like to calculate, right? Now, to calculate this, what should we do? So, so consider this picture for a second, right, where you see different colors. Every color corresponds to an epsilon or a different energy level. And so what we want to find out is, first of all, what is this structure epsilon pseudospectral abscissa, right? So for a given energy level, that corresponds to these values, the rightmost eigenvalue for the energy level green, right? In this case, that's going to be given by this worst case disturbance over here, right? Then as I change my energy level, right, I'm going to possibly increase the radius, right? And, that radius is given, or this abscissa is given by this worst case disturbance over here, which is right on the limit on the imaginary axis. For more energy than that, then we may have a worst case disturbance that makes the system unstable, right? So to figure out this blue value, right, we need to be able to find out what are these worst case disturbances, or in other words, we want to be able to solve these problems as a first step, right? And so this is the worst case disturbance for a given energy epsilon level. It looks like a complicated problem, and yeah, it is sort of. And but there is some structure to it, right? And this is an equivalent characterization. You can define a matrix which is given as a real part of a certain product. The product involves the left and right eigenvectors of the rightmost eigenvalue corresponding to the worst case disturbance. Okay, so if you think about it, okay, this equation is an equivalent characterization. It is an implicit equation because you have the delta opt on both sides here, right? It shows up here. So, but it shows a little bit of a structure. It gives you more information than the previous formulation. And certainly, okay, this is a non-convex problem. So what can we do here to try to compute this disturbance? So certainly we can take advantage of the structure, right? And observe that if we fix this matrix M, so for a given M matrix fixed, then our problem becomes convex and is linearly constrained. So we can try to solve this convex problem. And certainly you can figure out a solution. All right, so this is the idea of the solution. Because of the saturation constraints, the entries of this matrix are either going to be saturated, right, with the upper saturation or lower saturation bound. So that's the case. And when they are not saturated, they have to be proportional to a certain constant here that has this expression, and that the expression involves the energy level is discounting from the energy level the contributions of the saturated entries, and then everything is divided by the sum of these proportionality constants, okay? So, all right, so looks also complicated, but at least we have some sort of expression. Now, we can look at particular cases and recover expressions that are known. For example, here, when there are no sparsity or no saturation constraints, the worst case disturbance is something that should be proportional to this M matrix, right? And has the epsilon there, right? So it's the maximum energy, if you like. When there are sparsity constraints, but no saturation constraints, all right. It is another expression that basically, yeah, it's some sort of either or condition that depends on this matrix M and looks very much like this one. So, but still you have some nicer expression. In the most general case, this is the solution we got. And you can try to calculate that expression, that solution, right? And so good news is that you can do this through some algorithmic approach. And this is the algorithm, all right? Now let me explain what this algorithm is doing. So it tries to construct progressively the set of edges for which saturation happens, right? So initially you say, okay, there is not gonna be, no edge is going to be saturated, if you like. With that, you compute what will be this theta opt. And then based on this, you will update progressively the sets that need to include edges or entries corresponding to edges that will be saturated, okay? So that's kind of done recursively with some logic that you see here that exploits the mathematical expression for the optimal solution, okay? So you do this, and good news is eventually you converge to the expression of the solution. So you take my word for that. Okay, and that's great. Okay, so we were able to solve this first problem with a fixed M matrix, right? Now, this is not solving our original problem yet, because we want to solve the whole thing with them depending on the worst case disturbance and so on. But the structure gives us a way of approaching this by following one of these alternating directions methods. Okay, so what, like ADMM, like when you have a non-convex problem, what you can do is try to fix one component of the problem to make it convex, then solve for that and alternate, right? Keep updating those values. And this is precisely what this algorithm is doing, right? So you can think of, okay, I start from a given disturbance guess, right? A guess like delta K. Then I'm gonna find the corresponding eigenvectors and this matrix MK. Once I have MK, I can apply this intermediate algorithm, this incremental algorithm, and find the next delta K plus 1, right? And I can alternate like this, iterate, and see what happens. So what happens, I can tell you the following is that if you consider this iteration and the fixed points of the iteration, actually the solution will necessarily satisfy the condition to be an optimizer for the problem. So this is great news. But other a little bit more of analysis allows us to say that if you start sufficiently close to the optimizer, then you have a linear convergence rate to it, as kind of described in this way for some constant that is less than 1. Okay, so yeah, roughly this is the result with omitting the details of the R and everything. Now, let me show the results for a particular matrix case. Here you have a network, and the matrix is in a companion form. We assume that the attacks are going to happen over these red links, right? So you can try, for different levels, you can try to simulate, okay, what's going to be the spectrum of the whole collection of disturbances. And this is what you can get just by simulating this. You see how things change as you consider different energy levels, right? So for a small energy, all of the real parts of the eigenvalues are less than 0. So that means that the system that was stable, will remain stable. Then as you increase this energy, there's going to be a point where you just touch on the imaginary axis, right? So this is kind of the limit of stability, right? And then after that, you will cross to the other side, right? And you will have instability in this way. So this is showing, how this process goes. And what we would like is to have an algorithm that allows us to find this critical value of the energy, right? When things start to go wrong. So how can we do this, in general? That's the definition of this structure stability radius, right? And well, how can we do this? Well, an observation we can make from the previous simulations is that the structure epsilon pseudospectral abscissa, which is this alpha, is an increasing function of epsilon, right? So as you put in more energy, you start from negative, and then you will have you will cross when the abscissa is 0, and then you will become unstable, right? So this is basically the 0 crossing of this function as a function of epsilon. And so what can we do to find it? Well, we can try to use a numerical method, and the classical numerical root finding method is Newton's method that you can see illustrated here, right? And which uses information of the slope of this function, right? So if we start close enough, eventually we will be able to find the root of the function. Now, can we do that for this problem? And the answer is yes. So turns out the function is locally Lipschitz and differentiable almost everywhere. So when it is differentiable, this is the expression of the derivative. And here in this expression, you see that it is given in terms of this optimal theta that appears in the characterization of the worst case disturbance. Okay, so that's playing a role here, other than that is a function of epsilon. Okay. So, well, we could use it, right, in order to update our Newton step, right? And now, but however, it depends on the disturbance. So now what we have to do is create a larger compounded algorithm where we are updating the epsilon at the same time, we are running this method to get to the optimal disturbance per level of epsilon, right? And so that way we will find, hopefully find the zero crossing of the function. Now, yeah, this works. It works locally, also because the previous method has a local convergence guarantees, right? For us, it requires a bit more. So we need to ask, we need to impose that the rightmost eigenvalue of this worst case disturbance is simple, right? And then other than that, that every time that you initialize the incremental algorithm to find the worst case delta for a given epsilon, you start sufficiently close to the optimal value, right? If you do that, then you can guarantee convergence. And then you can characterize how this Newton method converges to the structure stability radius. So there is a characterization for that and a quantification of the error. And well, I mean, I can share with you that later if you like, but anyway, you take my word for the truth, and that's what eventually, we can guarantee. Now, let me show you how that works for this example. And we have tried other examples on larger matrices, but anyway, this is one easy example to see what's going on. So here on the horizontal axis, we have different energy levels, okay? And on the vertical, we are plotting values of the structure epsilon pseudospectral abscissa, right? And so we have this curve that you can find by simulation, computing it, for different levels of epsilon, we can do that. And now on top of this curve, we use this compounded Newton algorithm. And so iteratively, what happens, what we should see is that we converge to the value, right, that corresponds to 0. So if we get a 0 here and we go down, this value of epsilon is what corresponds to the critical stability radius. And that's exactly what we see here happening. Is a very fast algorithm, actually. And in just 5 iterations, even though we haven't characterized the convergence, well, we have a certain characterization of the convergence rate, but actually in a finite number of iterations, we see most of the times convergence to the value, right? And so that would give you the 14 that we saw in the previous slides. Okay, great. So this is one computational approach to this metric of resilience. It's somewhere involved, but also you can see a couple of things, right? So first of all is you need to know, to apply this analysis, let's say before deployment, right? Before letting the system out into the world, if you like, being subject to disturbances, and you need to do it with full information and with a centralized algorithm, right? But what happens if, well, that's not the case? You have deployed your system, it's out there, and now, there is a certain disturbance applied to it, right? Is there a way in which we can evaluate whether or not it's stable, right? And what motivates our second part of my talk on this decentralized computation of the network eigenspectrum. And so that's the case, you have your system, it's been deployed, it's subject to inputs, you get some outputs, you have a multi-agent system, and they would like to figure out, okay, what is the eigenspectrum of the system? So now then the agents interact over a network, maybe can collect inputs and outputs measurements, right, to try to figure out what's the A or the B here. And they can do, use some distributed algorithm on top of it. So, so that's what we looked at. And our approach to this problem is based on data-driven ideas, right? And basically using Willem's fundamental lemma, as I'm gonna show you in a second, right? And so these are the key observations to do this are the following. We have to figure A, right? So, and the spectrum of A. So I have an N missing here. So eigenvalues of A are the roots of its characteristic polynomial, right? As we all know. So if agents were able to know the characteristic polynomial, then they would be able to compute the whole spectrum of the matrix in principle, right? Finding the roots of this. Yeah, so that's the next observation. And another observation, right, to use data-driven ideas is that by Cayley-Hamilton, actually the matrix A is the root of the matrix equation set up with this polynomial as well, right? So this is great because if you take this expression and you multiply with the right observability matrices, right? Here we have a linear observations. Turns out that an unforced output trajectory of the system has to satisfy similar equations. Okay, so from here you multiply by the CIs, and then you will get all of this expression where you have a sequence of outputs, right, along time. And those are equations that need to hold. The Y bar, though, are unforced output trajectories. And this system is possibly, you know, subject to inputs because we are learning it, right? So anyway, so this is then the strategy that we take. We will use Willem's fundamental lemma to calculate these unforced output trajectories. And then once we have these output trajectories, agents have their output trajectories, they have a system of a linear algebraic equation, right? And then what they can do is solve for, actually the unknowns here will be the coefficients of the characteristic polynomial. And so then after that, they can get the spectrum. All right, and so this is a reminder of Willem's fundamental lemma, right? So as you may know, if you persistently excite a linear time invariant system for sufficient amount of time, then you can construct a type of a linear operator that is based on certain inputs and state variables associated to these inputs, right? So that the state variable trajectories and input trajectories can be expressed as a linear output of this system that I have here. Okay, so there is every G, every vector, when you multiply it by this Hankel-like type of matrix, will give you inputs and state variables, right, corresponding to these inputs according to the system. Okay. The matrices, the particular dimensions and everything I'm omitting here, but they have a form that looks like this. So it's something composed of data that you get, you know, from inputs and your states X, okay, Hankel-like type of matrix. So then using this, now you can think, okay, so I need to get an unforced trajectory, right? So then what I need to do is I set all of these inputs, right, equal to 0. I get G that produces these inputs, and then moving forward, I will get my unforced state trajectory. Okay, so that's the whole idea here. So in other words, right, I need to find the G, so that multiply with that is the right block here. I get a 0, right? And then, you know, from there I can continue, right? This is actually equivalent to this other set of equations where we are using the fact that agents can observe also the inputs that are being applied to the system, right? So we have a collection of input observations, if you like, given in this way. And so when we use these matrices E, we can find an equivalent characterization to this equation that uses the V, which is extracting these inputs, right? And if the E is full column rank, so this is an if and only if. Okay, so suppose we have the G, I mean, this is the goal. We gotta find the G that satisfies this, where now these are the VIs depending on each agent. Suppose you are able to find this G, then once it is found, we just plug it into the second part of this Hankel-like linear operator, right? We get a sequence of a state trajectory we get, right? A sequence of states, and then by a similar trick as before, but this time using observability matrix multiplication. So from this equation, we get to the second equation, and then we get the, individual observations per agent, okay? So that's kind of straightforward, right? Once we have the G, we apply this operator, and we have the enforced output trajectory per agent, all right? And the final step is, all right, once I have the enforced output trajectory, then I set up a final set of linear algebraic equations, and then I will have my multi-agent system solving for these coefficients. All right, so great. So we have been able to reduce this problem to solving various sets of linear algebraic equations. The agents are interacting over a network, and so this looks like a consensus type of problem where we have agents need to find the common solution of this set of equations, okay? And now agents can exchange some information about what's the current values of these C's and so on, eventually to convert to some consensus solution. And so this problem has been studied before, okay? So maybe you remember Steve Morse has worked on this, or Angelia Nedich, and this is a variation of, I think, well, I don't know if it's a very much of a variation, but anyway, the algorithm is like this. And you see it has the typical consensus form with a projection operator here, given by projecting, depending on the kernel of these matrices MI that set up the equations, right? And so on, right? So it's a typical type of consensus problem. And you can, prove easily, okay, convergence to a consensus value under the standard assumptions of consensus problems. I guess that our contribution to this problem was just, okay, for this case, a characterization of what's the limit value. So this is the limit value. This is the consensus space that we have a Kronecker product there. And then you can see that, okay, the solution is a combination of two things. A first contribution depends on the initialization, what are the initial conditions for each agent. This W is a Perron left eigenvector associated with the normalized adjacency matrix of the graph. And this one here is a minimal norm common solution to this set of equations. Okay, so anyway, we have the standard convergence result, and that's the limit what we get to. All right, so this is the summary of the algorithm. We need to have a sufficiently large time, get some data, right? And then the output will be, every agent has an approximation of the roots of the polynomial, the characteristic polynomial. To do this, well, first you apply LAE solver for this data, right? To get the enforced, the vector G. And every agent will get an approximately equal value of G that we call GI. Using this GI, okay, you plug it into this linear Hankel matrix operator, and then you get enforced outputs. And eventually you set up the last LAE with this matrix and this independent term. And then you solve, and then you get the coefficients of the characteristic polynomial. Every agent will have an approximately equal coefficient, although it depends on how long you run the solver for. And finally, once you have these coefficients, you compute the solutions, the roots, okay? And that will be the outputs. Now, you may ask, well, okay, that sounds simple enough. Is this going to work or not? Well, I mean, the whole approach relies on one assumption, and is that we have uniqueness of solutions. So in other words, when we find out this G, there is a unique G so that, it's gonna solve our equation, okay? And so, so that means, a G obviously that works is G equals 0, gives you, when you multiply by any matrix, it's gonna give you the input sequence is gonna be 0, right? So we want to avoid having that as a solution or having more solutions than those, right? So that then agents can, keep track, they are using the same vector and eventually they can do a good consensus on all of the coefficients of the characteristic polynomial and so on, right? So anyway, so this is, we studied some sufficient conditions that guarantee this. And so this is a controllability type of condition that we found. In general, I mean, how can you check these conditions if you don't really know what the matrix A is? So we looked into how generic these are. And so in the sense that, well, if you have a matrix A, any with probability 1, you are gonna, be able to satisfy the condition. And this actually happens under mild assumptions, really. This can be shown. And anyway, there's other things we see in the paper, for example, when we interconnect the system with other systems, but I'm gonna leave that and refer you to the paper. This is a simulation so that you can see how this works. This is a 6-agent network, and I'm showing you here what are the outputs and the inputs agents have access to. So not all of the agents have access to all of the outputs or all of the inputs, maybe just 2, right? And they are looking at a system that is 16 dimensional, all right? So, all right, so then to implement this algorithm, agents need to include some persistently exciting inputs at first, and then you can see, what the signals, how the signals look, and what the corresponding outputs are over here. And well, putting all these things together in this algorithm, this is how the estimate of the eigenspectrum looks like, and looks reasonably good. The estimated eigenvalues are very close to the true ones, and these are the errors, how they evolve. In general, the performance of this algorithm is going to depend on well, how fast these solvers work, right? And the convergence properties are similar to those of consensus algorithms. So that's the same type of limitation that we have here. Okay, so that's about that. Now, let me go back to this question of coming up with a defense against network attacks through a switching strategy. So we have, again, our linear time invariant system in continuous time. And then we have 2 types of actors here. We have an attacker that implements topological attacks, okay, general attacks in modulated by this attack signal omega of beta. And then you also have a defender that modulates defenses through the signal nu, right? And so really our ultimate motivation that I cannot really go into a lot right now is what we wanted to see is how these defenses really influence the structure stability radius, right? We wanted to see an increase in stability. And that's what I don't have a complete answer to this right now, but this is what we are thinking about really. Instead, what I'm going to show you is, well, okay, a particular defense strategy based on some switching ideas and how it plays out here. But really, this is what we wanted, what we wanted to answer. Okay, so to explain this, I need to lay out assumptions on attack signals. So what types of attacks we will have? So these are going to be right continuous and piecewise Lipschitz. The attacker space is going to be compact and convex. So you can imagine you have a hypercube, and there's going to be a minimum dwell time for attack switches. All right, so we need to have that variable there to be able to say things. This is the information available to the attacker. So the attacker will know the whole set of system matrices. They also know what is the evolution of the state a long time and what the defense signal is. So knows pretty much a lot of information. And then these are the assumptions on the defender side, right? So the defense space we are going to assume is convex. We are also going to assume that the problem can be solved. So for every attack, there is at least a defense. And that translates into this Hurwitz condition, where here is like, for every omega hat and nu hat, this is Hurwitz. So, I mean, the reason why we put this here is to have like a common lambda max, right, for any pair. And then the defense signal is right continuous, and it will be piecewise constant in this case. The information the defender will have access to is all of the system matrices. They will know the state evolution and the rate of change. The defender knows the attack space, but doesn't know the attack signal. All right, so what can we do? I mean, objectives that we would like to achieve are, well, first of all, we would like to identify what is a finite set of candidate defenses, right? So based on this, we are gonna use this to define our piecewise constant switching defense signal, right? And what we would like is, eventually we would like the system to be globally exponentially stable by this. So we are gonna look for conditions that can guarantee that. And so first objective is feasible, right? Under the assumptions we have, I can tell you that we can partition the attack set into pieces so that for each piece of this partition, there is a defense action constant and positive definite matrices PI hat, so that this Lyapunov condition holds, right? Which will be a good condition for guaranteeing global exponential stability. Okay, now how do we find this? No, this is feasible, we can actually find it. And the approach is to, well, trying to find this common quadratic Lyapunov function is how we end up having this partition of the attack space. All right, so what we would like is to have a very robust strategy, and we would like to be able to solve this problem for as a large part of the attack space as possible, right? If we could achieve this, with a single shot, no matter what, we would have our guaranteed stability. But what happens is that maybe this is not feasible in the whole space, at least not with the rate that we would like. So that forces us to partition this, break this into pieces, all right? Now, you may ask, well, okay, this problem is non-convex, it has bilinear matrix inequalities, and yeah, it's correct. What we do is use an SDP approach, right? And find a local solution. I mean, there's a solver available in the literature that was proposed not very long ago that allows you to find a local solution to this problem. And for us, a local solution is enough, right? What we want is to be able to satisfy this constraint. This is the most important part. All right, so this would be how this algorithm works, partitioning this space, right? So you first aim to solve P1 for the whole omega, suppose it's a square, but now suppose that there is no solution with a lambda star that is at least a lambda mean, right? That we want to to make sure we have. So then, if it's not possible, then we bisect the square into pieces. And then we look on each of the pieces, right? And we try to solve the problem again there. If there is no global solution for each of the pieces, then we cut it again in two, right? Then maybe, I don't know, we are lucky and we have a big chunk of the attack space for which we can find a solution with a good lambda star, and we have a nu star, right? So that would be the strategy that works for that piece. But maybe there are other areas that need more refinement, and so we keep doing this over and over, until some point. You may ask, well, is there, will we have a guarantee of a final termination? And the answer is yes, if you impose that this lambda mean is less or equal than the lambda mass that appears in that Hurwitz condition on the, for every attack, there is a defense property, okay? So yes, that can terminate in finite time. So with this, we would have identified our final set of candidate defenses. And now the next objective would be, okay, define a switch triggering mechanism so that the defense signal makes the system globally exponentially stable, right? And so there are things that we look at, right? So first of all is, okay, we're gonna be monitoring the system evolution, evaluating its stability somehow, in order to switch strategy. I mean, that's the idea, right? Natural idea. And so in this situation, we say, well, this monitoring, this evaluation is gonna require some effort, right? So then it's going to, since it's going to take us some time until we realize that we have to eventually switch, right? So that's gonna impose these delays, right? And so whatever we come up with, we have to be mindful of this implementation delay of the switch, yeah? And then a difficulty that, well, I mean, to some extent we have addressed, but not completely, I would say is, well, we are gonna be switching, but the adversary may also be switching, right? And so in this delay period, it may happen that the attacker just wants to switch, in the middle of this transition period, right? And then you're gonna be forced to maybe switch again, right? Before you have switched. And so this situation is possibly going to lead to instability, right? And so we cannot handle the most general case, but we find conditions for which this at least can be addressed in some cases, okay? So, so anyway, I'm just gonna give you a rough description of this. I don't have a lot of time to go into really the details, but anyway, I'll show you some boxes, I guess. First, regarding on the monitoring of the system evolution, well, I mean, what we do is precisely we use the Lyapunov functions, the P's that we found through this partition, okay? So that should satisfy this equation, right? That's for omegas in these pieces of the attack space. So that's what we can use to use as a index that we are evaluating. Our criterion to switch is gonna be based on this, right? So if we define this quadratic function, we take this derivative, right? The right-hand side, encodes the rate of change under the dynamics of this U, and this is used to evaluate the stability, how stable the system is under our current strategy. And so, so basically, right, you have these functions, you are monitoring. If they are not decreasing fast enough as you expect, that's marked by this time, then, I mean, that's the point where you want to switch, right, to a new strategy, right? Now, the thing is that you realize of this later after a delay, right? That would be the how this policy is defined, right? So essentially, you want to switch once you realized, okay, I'm not decreasing well fast enough. And so where do you want to switch to? So you want to switch to the best possible other strategy that will lead to the fastest decrease, right, in your change in your Lyapunov function, right? So that's what you would like to do. So this is what this is encoding. And then, okay, here just a quick summary of results, right? So if there were no delays and you had just a constant attack, right? It's immediate, it's very easy to show that you are doing the right thing, you have this property which is helpful for stability, right? Second property, okay, suppose you have these delays and these delays are bounded in the right way. Here there are many constants that I don't explain what they are, but they involve the Lipschitz constant of the attack signal. These C's depend on the system and the attack matrices, okay? And here what is important is that suppose the attack signal is Lipschitz over the time period from S to S plus tau D, where you are realize you wanted to switch. So if that's the case, then you have the right, you can ensure the right condition for stability when you switch, okay, which is this inequality. Now the question of what happens if the attacker switches when you are exactly in the middle of the delay, right? That will call for another switch. And so this is what we can say, right? So I mentioned there is a dwell time between switches of the attack, right? And so if this condition holds, so at least the dwell time is twice the delay implementation time, and that's not enough. And the switching, right, is slow enough, right, in the sense of a certain average dwell time of the defense signal, right? If those two conditions hold, then you will have the stability properties that you are looking for. So this is a long story, also lots of constants here, but just, this is a property eventually, okay? So anyway, so we need to, ask these conditions, and obviously, in a simulation, I can show you a case where this is gonna, if these conditions do not hold, then you have an unsuccessful defense, right? This is for a simple network of 5 agents. You can see the attack signals are the omega-1 and omega-2, so it's 2-dimensional, and then we have a defense single value given here by nu, and basically these are making stronger or weaker some links in this network, right? If you do this, finding the finite set of strategies approach by this bisection, you indeed see finite convergence after a number of times, and these values in the boxes are the values of the nus, right, that we would have to use. And then, okay, so then now you can look for attack signals that satisfy the properties. You see the delay here is 0.5, and the dwell time between switches in the attack is 4, so it's well over twice the delay. This eta has to do with the decay rates in the stability properties. And so here the interesting thing is that the attack signal, the attacker in one of the components is trying to approach always the worst case attack. So that connects with the first part of the talk, is trying to reach to this delta worst case by changing linearly, okay, getting there. And then, well, I mean, the effects are these. So this would be the trigger piecewise constant defense signal, which has a delay. As you see, there is a shift. And these are the effects on the system stability. So because of the attack, there's going to be some overshoot, there's going to be later some settling time, and eventually it will come back down to be stable. And that's one, simulation for a choice of parameters. But then you can, you can try to push the system and see how bad this becomes, right? As the Lipschitz constant of the attack becomes larger and the delay becomes larger, you are gonna get, instability here, right? The overshoot is going to be just unstable. This is regarding settling times and number of switches, right? Again, as a function of L and the delay. For example, in the number of switches, you see how they dramatically will increase. So basically, the system is becoming unstable, right? With so many switches. Okay, so that brings me to the end of the talk. So I presented you 3 different works related to network resilience, how to compute these metrics through algorithms in a centralized, distributed way using data, and then a particular switching defense strategy that exploit the idea of common Lyapunov functions. Future work. Well, all right. So if you look individually into this, there are questions that you can think about. Like, for example, what if you have, regarding the second, right? The second one is we use Williams' fundamental lemma, but this requires perfect output measurements so that these results apply. If you have noises there, actually this technique that I show you is super sensitive to noises, right? So the question is, well, how to make this more robust? Well, I don't know how to do that, but that's a limitation of that. Defense strategy based on switches, right? So it assumes perfect estimation of the state, but what if there are errors? That's going to have an impact, right? I think that the most, as I said, the most interesting question is relating switching to the making larger the structure pseudospectral radius. This is what we really want, and we still are trying to figure out. And then, okay, the defense is also centralized, so how to make it distributed? It's also an interesting question to look at. Okay, so that's it. Thank you very much. Hopefully this was not too technical, and I'll be happy to take any questions.
Thank you so much for the great talk, and we'll have time for questions. We'll start here in the physical room. Oh,
yeah.
Yes, I can barely see you actually because.
So I have a couple of questions, but so it seems, so if I understand correctly, you're trying to defend an attack against an attacker that's trying to make the eigenvalues move into the positive right-hand plane. What if, though, instead an attacker is trying to make the solutions non-unique, so the system is not observable? Is that possible? And would that mess up, cause problems?
Yeah, so I think the uniqueness of solutions is important for solving the second type of problem, right? The distributed calculation of the eigenspectrum. Absolutely, everything will break down. However, the conditions for uniqueness are very mild. So almost any system will lead to unique solutions. Anyway, so if an attacker has precise knowledge of the system, it may lead to to a case where there are multiple solutions with multiple G's, and that for sure will will make things break down. Now, it would be interesting to see, I guess, if it's possible that some agents believe there's stability and others believe there isn't, right? Yeah, and what would happen then? But I mean, then you would have to address that in some other way, right? So it's a good question. Yeah, it will certainly mess things up. Yeah.
Interesting. My other question is, so it seems like the bisection of the attack space, how does that scale? It seems like if you had a lot of dimensions, that would scale poorly. Is that true?
So yeah, I mean, the more dimensions you have, right, the more divisions, right? This is going to increase the the computation is going to have an impact on scalability. You are right. I don't know. I mean, we haven't fully explored it, you know, to the full extent to see how bad really this can be. But yeah, definitely, it will have an impact there. Yeah.
Thank you. This is a really interesting talk. I enjoyed it.
Thanks.
Other questions?
Okay, I have one. I'm afraid a more basic question.
Okay.
It's a great talk, and I followed kind of like to catch up with everything there. I kind of miss the not idea behind the word, but idea behind the matrix A. Like there is this x dot equal ax plus bu. So I understood that there is a learning of agents, like trying to.
Yeah. So the idea there is you don't know the matrix A.
Yeah.
Right? The matrix A has already been, you know, you have deployed your network into the world.
Okay.
And somehow it has been disturbed already. So that A in the second part is like A plus delta in the first part. And you don't know it. And then what agents can do is they can get output measurements of the system. And also they have access to inputs. So what inputs are being injected into the system. And they have these data sets, right? And with those data sets, you can actually reconstruct the matrix A. Yeah.
So what the so that's exactly you pointed exactly where I wanted to what I wanted to. So if I take that matrix A, so it has some, you know, rows and columns. There are certain numbers there. So what are these numbers physically? Is it actually important that at all? Is it like this is like an abstract question of like abstract research about potential to estimate something like a matrix A, or there is actually some real like physical value, like A is like an I don't know, number of packages sent between two nodes, or can you give me like or give us some idea about what
can A model?
Yeah, exactly. What is behind? What is the kind of physics behind it? Yeah.
All right. So A, you know, can model, yeah, as you said. So the easiest thing to say here and answer is yes, it could model an information exchange between nodes in a communication network. Yes.
Okay.
It could be the flow of, you know, packages sent from one node to another. I see this as you know, the system is linear, right? So I think any flow type of network, right? And in a first approximation can be modeled by means of this linear model. And so, yeah.
Yeah. So is it sensible, for example, to create a couple of nodes, even like on a single computer, like you create multiple processes, and you kind of establish some communication links, and then kind of, I mean, does it make sense to do, or do you think that the story will change, or you firmly believe this will really hold? I mean, not questioning the technical aspects of matrix of the work you showed us, but what really matrix A represent?
Yeah. I think yes. Like if a linear system like this would be a good approximation of the setting you mentioned, I think so. I think so. Then with one, I mean, it would be better if it was like, you know, a time varying type of approximation, right? If you want to think of a more real communication system, you know, those links possibly are changing with time.
Right. Okay.
Yeah.
Okay. Yeah. Okay. Well, yeah. Thank you for the the explanation.
Thank you, Dejan.
One more.
Other questions? Other questions for Sonia?
Yeah, I have one more. So you have two assumptions. One, well, maybe more, but so you assume that you can start close enough to the optimal point for delta that you can reach that. Is that something that is actually easy to do in practice to sufficiently close estimate, then also you assume that the attacker can't switch faster than a particular rate. And is that something that you can enforce somehow in a whatever system you're trying to apply?
Okay, you are asking two questions, and it seems to they refer to two parts of the talk. Right?
Yeah, they are. Yeah.
The first question is the initialization of this delta worst case, to find the worst case type of disturbance attack, right? And how, so that I don't know, it's local. What can I say? One would have to study, I guess, the extent of the non-convex. The problem is non-convex, that I can tell you for sure. So how important it is? Well, as in any non-convex problem, yeah, it is important to start close to the optimizer in order to get to it, right? But beyond this general statement, I cannot really tell you anything else about the problem. I don't know how things will change from matrix to matrix, for example. Yeah, I mean, well, actually, we have looked a little bit into the sensitivity of the problem to the parameters in the paper, that I think. And I think, yeah, what was the conclusion there? We said, I mean, it was not the dependence on the parameters was somewhat smooth. So we could have these stability results hold, even the local ones. Otherwise, you don't even have a local convergence result. But beyond that, like what is the basic, how non-convex the function is what will help me tell you how important it is to start far from this optimizer, and I don't know. Okay, and then the other question is about the switching, right, of the attacks. Yeah. So so what was the question again? So whether we can prevent this? I mean, the question is, I guess, if you have an attacker, is very powerful, knows what you are doing, right? This is a possible way, switching fast, switching precisely in between in those delay intervals, right? They can exactly do that, and they would just mess up with the whole thing. Now the conditions we have in the theorem, right, on the average dwell time, right, is like the defender itself is not switching very fast, right? And so that indirectly actually is imposing a condition on the attacker that it cannot switch very fast either. So they are kind of a linked conditions there. But so somehow indirectly we are assuming the attacker and the defender, both of them are not switching crazily often. And then in this situation, things work. If we don't impose those conditions and the attacker can do virtually any switching and the Lipschitz constant is very large, then I mean there's little I mean, we don't have a characterization better than what we currently have that guarantees stability. And you can see in simulation that for sure things are going to break down if you violate them, right? And yeah, beyond this, I cannot tell you much more. I don't know if this helps a little bit understand the setting.
Yeah, I guess it makes sense that there's limits on how fast an attacker.
Yeah, there is limits. Everything depends on limits always in these adversarial problems, and then the question is how much, what characterizing our limits, right, with respect to the adversary, how much we can do. And there's always a situation where there's nothing we can do. I mean, the attacker could be super powerful, super knowledgeable, right? And in that case, what can we do? We cannot do much.
Okay, thank you.
Any other questions?
Well, I think we have abused our speaker enough, and we'll thank Sonia again. Thank you so much for the presentation.
Thank you, Ricardo, for
And
the invitation, and thank you for coming to the seminar.
yeah, very, very well attended. And I will need to go to teach, and I would like to thank everyone for participating, and we will see you at the next seminar that we will announce. And Sonia, you deserve a break, and then Santiago will take on in the same Zoom link. So I hope the meetings go well, and I will connect after the meetings
Yeah.
with everyone. Thank you.
Thank you, everyone.
Are you already logged in?
Yeah. See you later.
We stay I stay in this link, right?
Yeah, thank you, Sonia.
Yeah.
So we've got Santiago, he's a grad student who's going to talk to you first, and then it'll be Dejan and Alvaro. So you're going to stay in this Zoom link. I've made you co-host. Santiago will join you shortly. I'm going to turn off this room camera, but he's already in the Zoom room with you, so it should be good.
Okay, sounds good.
See you later.
See you now.
So are you turning it off?
Yeah, I'm going to remove it.
Awesome. Thanks. Let me check if my sound is working. Hi, Professor Sonia, can you hear me?
Yes, I can hear you.
Awesome. Yes, thank you for the really interesting talk.